Yes, sir, please start. Yes, good evening, everyone. I, Mani Khanna, on behalf of ASHRAE Chandigarh chapter, welcomes you all in this webinar, in this 20th webinar, basically, which is organized by ASHRAE Chandigarh chapter and ASHRAE India chapter in association with ISHRAE Thane chapter and India. So the topic of today's webinar is impact of climate change and urbanization on future building performance. So on behalf of IPSA India, I would like to invite Dr. Jyotirmay Mathur to introduce the speaker and represent the IPSA India, please.
Thank you, Mani. Good evening, everybody. Good morning, everybody. Especially for those who are attending from US, I'm told there are few participants from outside India as well. So we have the privilege of having a very eminent person as speaker today, Dr. B. Crowley. Uh, we popularly call him Drew Crowley. So uh, Drew is actually a very renowned person in the field of climate change and building energy performance simulation. He's fellow of ASHRAE. He is Bentley Fellow and Director of Building Performance Research with Bentley Systems, focusing on building performance, BIM, zero energy buildings, resilience, sustainability, and smart cities. He has more than 40 years of experience in this field. Dr. Crowley has a very active association in ASHRAE. He is the chair of the famous ASHRAE Standard 169, which is related to climatic data for building design standards. He is member of several committees on ASHRAE. He is also very active on IBPSA, International Building Performance Simulation Association. He is vice president since 2018, and he has been president of IBPSA USA. More importantly for Indian subcontinent, Drew has been very actively involved right from the time when energy efficiency in building started to become important in India. He was very active on few of the USAID-led projects, and he had active association with Bureau of Energy Efficiency and many government organizations. He has been instrumental in many policy formulations related to energy efficiency in buildings in India. And one more important thing, there are a lot of important things, but one more important thing is Drew was author of one very famous paper that had presented a very critical comparative study of more than 50 energy simulation tools, and that was very widely read. In fact, to my understanding, that was the most widely referred paper within the community of building energy performance simulation. So it's indeed a proud privilege to have him as today's speaker. I would not like to come between you and the words of wisdom to be shared by Drew with all of you. So I end his introduction here, although it was highly sufficient considering his credentials. Over to you, Mani. Thank you.
Thank you very much, sir. So the today's before starting the webinar, in all ASHRAE meetings. So in this and all other ASHRAE meetings, we will act with honesty, fairness, courtesy, competence, inclusiveness, and respect for others, which exemplify our core values of excellence, commitment, integrity, collaboration, volunteerism, and diversity, and shall avoid all real or perceived conflicts of interest. So before presenting directly to the topic, so I would like to invite Mr. K.K. Mitra from ASHRAE India chapter, who would like to add something from ASHRAE point of view, please. So you are not audible, please. Mr. Mitra, you are not audible. Okay, so yeah, now proceeding with the today's presentation, I would like to invite Dr. Dhuri B. Kral, who is PhD AI Fellow ASHRAE, have been already introduced by Dr. Jyotirmay Mathur. Now I would like to invite our today's speaker, so on the great topic, which is impact of climate change and urbanization on future building performance. So over to you, Dr. Dhuri, please.
Okay, can you see my screen?
Yeah,
Okay, excellent. Thank you, and thank you for the kind introductions and the invitation from Chandigarh chapter initially in sponsorship with India chapter and ASHRAE Thane and ABIPSA India. I'm very pleased to be able to present this today. I wish I could be there in person, but hopefully soon. This is presentation that's been interesting for a while. I've had it to give for quite a while, but just recently it's been much more what people want to hear. So we're going to talk a bit about climate change, but I'm going to talk about specifically some of the uses of climatic data within within buildings and design aspects as well, and how that is affected. This is available for continuing education credits. These are specific to the US, but others can do as well. I'd like to start all my talks by talking about why we even care about energy performance. And around the world, buildings account for about 40% of energy use, and that also reflects about 40% or more of the emissions. Globally, buildings are responsible for about 70% of electricity use as well. It varies quite a bit around the world. If you go to I guess the fifth bar in that third group there, China, Hong Kong, India, you see that India is in the range of about 30% for buildings, and it has been growing. It's actually higher than it is in China, and it has been growing quite a bit. If I look back, for example, at China from 20 years ago, where now they're showing 15% energy use for buildings, that was only in the range of 5. The massive construction that is going on around the world is really changing the relationship. And if you go to the far right with the United States, for the US, we are at 40% for energy use in our buildings, and that buildings are a key component if we're going to deal with emissions and really a decarbonization activity. It's impossible to get there without really tackling buildings. Within that, if we look at the three sectors, transportation, buildings, and industrial, industrial in the US used to be the dominated part of our economy, but our economy's moved from inefficient, heavy industrial processes to much more efficient. So producing a ton of steel now takes much less energy than it used to. And same's true in many of the processes. Of course, the globalization that's happened is that many of the industrial processes are no longer just in the US, and that's a good thing that we are working around the world with many other partners. Our transportation is relatively efficient. We have good standards for surface transportation, and that has been consistent about 30% or so. Buildings, on the other hand, has been growing and split roughly between our houses and our half and half between commercial and residential. But the important thing to note is the differences in how we use energy, and that has changed quite a bit over the last 20 years. Yes, this is for the US, but heating is still dominating, water heating, cooling, lighting. and then appliances in our household. But if you look at the bar at the bottom, a full quarter of our energy now is from other things, small devices. It's the electronics, the phones, all the devices that are occurring in the house, and that has been growing in use. But overall, because the appliances are becoming more efficient and all our other uses are, energy use in the residential sector has actually been pretty flat for the US. In the commercial sector, of course, there's no typical commercial building. A supermarket will be where it shows refrigeration at 10% overall. In a supermarket situation, grocery store will have over half of their energy is related to refrigeration and freezers, trying to keep the food products cool and safe for us. But it's changing. Lighting used to be a much higher dominating part, but again, a full third of the energy use, as the bar on the bottom shows, are now related to our other uses, the small devices in our house that are contributing to energy use. So let's transition to weather data and climate. Not the same thing. They're kind of different aspects of similar pieces. Weather is what's happening right now. It's what you see from on your mobile phone, the temperature, the humidity, the wind speed, the rain, whatever's happening right at the moment. Climate is the composite of that over a long time. It's the prevailing conditions for a location or a region for what would be described as normal. In meteorological circles, they describe normal, and what the normals are, they are a snapshot of the past 30 years. Currently, we are not quite to a period where they're about to change those, but the normals for that are reported by the weather station, and I'll show you some of that and a bit more reflected in data, are from 1990 to 2010 at this point, or 1980 to 2010. So they are a snapshot of that data set and what is a typical range for the variability. Of course, that doesn't capture the day-to-day, but we'll be updating, or they will be updating that soon. Weather data is quite variable. This is from sunrise to sundown at the National Renewable Energy Lab, just one day of data, and you see it's changing. This is minute by minute data. The green line that kind of rises in the middle and varies a little bit and then gets about halfway during the day and then drops off. That's the solar radiation. And so we're getting direct sunlight in the morning. There's some intervals of clouds that intervene, and then in the afternoon it gets cloudy. And that's actually pretty typical of that location, that in the summertime it'll cloud up and may rain, it may not, but that's not unusual. We also have the wind speed at the bottom varying over the day. The top line is temperature varying over the day, and then the dew point temperature, the darker blue there, kind of in the middle. So the snapshot that we look at weather data is it actually not representing this well. The snapshot that we typically have from most weather stations is hourly data. We're lucky if we can do more, but our buildings are affected by all this inter-hour variation as well. So we need to keep that in mind, that our buildings are reflecting on all the changes that are happening, not just the changes at the hour point. New York Times for a number of years now has been doing a really great set of how hot or how much warmer was your city. And 2016 was the hottest globally on record. And you see the red there, that's 2016 data for Delhi. The gray that's kind of behind it are the normals. And what you may notice is the data or the actual conditions were much warmer February, March, April, May, until July and August, and then again September, October, and November. So we're seeing temperatures into the 30s and even a couple into 40s there. For the New York Times, they didn't have the data to show the all-time records across here, but so I want to show you what it looks like in where I am in Washington, D.C. So you see you have two gray areas here. You have the grays that are kind of the normals behind it, and then the lighter gray of the background are the records. And so the temperatures you're seeing there are, in many cases, this is 2016 for Washington, D.C. You'll see in March, there's a record high temperature, and I'm sorry, this is in Fahrenheit, but of 28 degrees in Washington, and that's just, it doesn't get to 28 in Washington. And then a little in the summer, a couple high temperatures in the high 30s, and then, but we're seeing high temperatures in September and November, and even in November, that temperature of 29 is just unheard of here in Washington. So we are seeing new highs. They're tending to be much higher than that regular time. The second hottest year was 2019, and at this point, they did have data for Chandigarh. The average temperature for that year, though, in Chandigarh was a little bit below normal, about 0.3 degrees. So you see temperatures kind of mostly in the range, except some going outside of the normals in kind of late May and June there. If we look at Delhi, Delhi was hotter, was actually a degree above normal. And so much hotter beginning in March, going into May, continuing into June and even into July. So the temperature, by September, the temperatures have gotten back into the normal range. But this is the sort of change we're seeing today. Some of this is related to climate change, some of it is urbanization, and it's a bit difficult to decipher which are separate. So this is a created by a group called Berkeley Earth. They share these data, they collect data from around the world. And what we've got here starting in 1850 is what data is possible to obtain for each year, what the average temperature was. You saw early that we had gray. That's because there was no data related to that area. And that's why you'll see a lot of the studies will start in about 1880 when there's consistent global data. You'll see across the bottom, though, there is the moving 12-month moving average for that data. And you'll see it warm up, like the late 1940s and the 1950s actually was kind of warm in the Northern Hemisphere. And 1970s cooling off a bit. But then as we get to the 1980s, we're going to stay above that line. The global mean average for that period is continuing to go up. You see the whole globe getting oranger and darker red, and here it's going to slow down the last few years, but it's now showing that we're on a consistent upward trend. It's not the typical down a decade, up a decade that we've experienced regularly. And there are, in the record, there are hot periods and cold periods that we can see that are measured, but we don't have global data going back far enough. But you can see that even globally, if it's a hot, particularly hot year going through 2018, there are cold spots on the globe. So it's not a consistent overall temperature change. But by 2018, we're already seeing about 3/4 degree average temperature change worldwide. Then if you do the same thing, Berkeley Earth hasn't updated their graphics yet, but 2019 was hot, particularly in the Southern Hemisphere. We saw temperatures well into the high 30s and 40s in Australia. Remember the fires that were so bad that were exacerbated by the high summer temperatures there in Australia last year. but for much of India, except the southern part, it wasn't as hot as the other. Africa, big portions, China, Southeast Asia as well. The US, it was not the hottest year, except in a few places on the East Coast. The other thing we're seeing is impact on sea ice, and the graphic is interesting to see the change, but what has happened, if you look at the bar on the left, it starts at about 25,000 cubic kilometers, and over that period is a 20-year period or so, is dropping to 15. So we've lost 40% of the sea ice there at the North Pole. And that's important because it's one of the climate regulators that helps the jet stream and other pieces regulate. Other things we've seen, anomalies, the one on the far left is is from 2017, where we were seeing temperatures in excess of 10, 12 degrees at the North Pole in the winter, which was very unusual. There, Australia, with the extreme high temperatures in the 40s, unusual back in January. And then even in the US there, the East Coast, we were seeing temperatures 10 degrees above normal in January. Almost a snowless winter here for the US, which is very unusual. If we look at 2020 so far, Russia, Sweden, Finland had an incredibly hot winter. In fact, this is Helsinki temperature. They have data back, the monthly temperature in Helsinki. And in 2020, it never got to freezing in Helsinki. Normally, Helsinki will have a meter, meter and a half, 2 meters of snow on the ground in January. The pictures I'm seeing from Helsinki from friends there at that time, there was no snow. So it's just a particularly unusual year. The Antarctic just hit 18 degrees in this past January. It's warmest temperature ever recorded. So we are seeing changes globally here. In the US, we were seeing, as I showed for 2019, but also 2020, difference temperatures about 5 degrees in some places. And then so far this year, Asia and Eastern Europe also experiencing abnormally high temperatures for this region. But as you see there, India was a bit cooler than normal. So it does vary region to region. But then again, we have 2020, and we'll yet to see what happens here, but you can see the emissions that had been quite so high. We're now seeing emissions that were due to COVID and the shutdowns we've seen globally that are taking us back 20 years to 2020 or so in terms of emission rates. And it varies by industry and what's going on. If you look by region, China, when they shut down early, almost 10% reduction. There, India, when your shutdown started in March, and Europe, Britain, US, and other countries. So overall, almost 20% reduction in carbon emissions. If you look at it by sector, surface transport in the US, it was even more. We were seeing about a 60% reduction. Most people are staying home. Less demand for power as our commercial businesses are not requiring as much. Industry off. Aviation, I read the other day, they keep track of a number of people going through on a daily basis in the US. The number of people going through the airports was off by 95%. So there are still flights going, but they're very, just nothing like that. So residential use as expected, as we're all home and using our electronics to try to look at things. So let's get back to climate. this past year, a second edition of a book, Building Performance Simulation for Design and Operation, was published. And there's a chapter in here that I had the honor to author on weather and climate and building performance simulation. If you're interested in a book that goes through lots of detail for various topic areas, this is a great book for that. It's not a textbook per se, but it'll give you an introduction to many different topics within the building simulation world. From that book, we talk about different applications and what you need. So energy design, compliance analysis for energy standards, typical full year hourly data. We may need other things. We move down equipment sizing, design days of short periods. If we go further, natural ventilation, local wind conditions, because wind is highly variable, dependent on obstructions and other buildings around. So it's very difficult to get the data. Most of our data sources are at airports, so it's important to know how the winds go right at the local area, not depending on the weather file. Also, daylighting study, looking at more detail than hourly illuminates. Renewable systems, you need the spectral variation of the solar radiation as well. So different sorts of things that we need that we're using to do our analysis in buildings. And so climate data has been one of those things that's been very difficult to get. As you saw in that initial slide, even getting global annual average temperatures has been difficult till recently. We have mostly from around currently 20,000 ground observing stations internationally. It rarely includes solar data. There are a few solar stations spread around the world as kind of truth to be able to compare to other things. Temperature, humidity, wind speed, and direction are usually pretty robust because the main source of this data is for aviation, and they need to know temperature, humidity, wind, and wind direction. And that's where we see that, but wind is not a particularly robust in terms of it being like you would see in a city. You're lucky if you get complete other data in many cases. One of the interesting things is the availability of now remote sensing or satellite data and some of the what they call reanalysis projects that are taking that and combining lots of data sources to pull together and create a new data set for us. I'm working with NASA right now. They have been working with a data set. They hope to make hourly data available. They will have they have data back to 1980, but they think the data is best and most robust about 2000 to present. It will give a gridded product eventually down to about 50-kilometer grid, which will give us data essentially anywhere on Earth. It is very good. We've been working with them within ASHRAE, within the technical committee. The data, they can match the design conditions within about a half a degree or so, just with the satellite data, which is pretty remarkable. It's not dependent on ground stations, but it actually uses the ground station data to improve the results. The master data sets worldwide are actually quite good. They're near real time. The US, NOAA, and its National Centers for Environmental Information are a repository for data provided worldwide to the WMO. And so that data is provided freely. It's normally updated daily, and it's a great resource for that. But the design conditions we use to do equipment sizing and look at the long-term aspects of that, we've got to do some polishing or review and calculations of the data to make sure that it's clean and very usable. And so we've got to create design conditions based on some historical record, and we have to do something about solar because 99% of the weather stations do not record solar radiation. So if I'm talking about design conditions, now I'm talking about those that are in the ASHRAE fundamentals. Used all sorts of HVAC applications, as well as residential, agricultural, industrial processes as well. Usually there'll be data related to dry bulb, wet bulb, dew point temperature, wind speed and direction. And these are based on that station data that are collected. Typical percentiles used, 99.6 for heating and 1% for cooling. Now, what do they mean? My notes there at the bottom say it, but a percentile is just the number of hours that you can expect on a normal basis that the temperature will be exceeded. So 99.6, only 35 hours a year will it be colder than that temperature on average. That doesn't mean every year. In some years will be less, some years will be more. Similarly, the 1%, it'll be 88 hours a year that you can expect the temperature to be warmer. So that is that's what all the percentiles are. Depending on the application, you may want to use other variables. The design conditions include wind speed, dew point, wet bulb, enthalpy, all sorts of different combinations there, so that you can see if humidity is more of an issue for you. You might want to start with some of those humidity variables instead. The monthly percentiles are also available for cooling design conditions, and TC 4.1, which is ASHRAE's load calculation, is recommending use of those. And the reason is traditionally in Northern Hemisphere, we did it based on season. So it was, the hottest January, and January was coldest and July was hottest. And the idea here is that instead, there may be other periods that are more indicative of a combination of not just temperature, but also solar radiation. For the US, September actually winds up being often a peak cooling month because the solar angles are lower, and also the temperatures are still kind of high. So monthly percentiles are also important to look at. The best source is the ASHRAE Handbook of Fundamentals, 8,118 locations throughout the world. That database provided by, it's now NCEI, the National Center for Environmental Information, is the source of that. That's that WMO data source. The handbook currently has 1990 to 2014 data, and we are currently finishing up the 2021 handbook, another 1,000 locations in there, and that data will be up through 2019. We're able to get data more up to the calculation point. The study was done a few years back comparing design conditions. This was from the 2009 handbook, and looking at temperatures. So the heating dry bulb temperature was up about a 1.5 degrees, then the cooling about 0.8 over that 20-year period. So we are seeing it in the design conditions already. From the 2017 handbook, these are looking at the dry bulb min, max, and average for that, and looking at the trends that you're seeing. And in all cases, there was about a 0.05 degree change per year in all three of those variables. Now, it varied in both directions, and all sorts of reasons for that, but we were seeing distinct change in the bulk of the data. The locations, North America, Europe, pretty well spread. Africa, a lot of gaps. Also, the same is true for South America. Not bad representation in India, but still not as much as could be. That continues to improve. With the handbook comes something called Station Finder, and the numbers here represent the number of stations that are kind of within that area. And you can go into Station Finder, and what I'm going to do is show you how we can zoom in to Chandigarh and see what data are available. So Chandigarh, they're kind of in the top left, and what you see is a number of green squares. Delhi has 2 stations, but there are a number. Lahore has several here. So these are the where there are data in the ASHRAE handbook today. So if we look in at Chandigarh city itself, there's no data. Patiala, not too far away, is not quite the same elevation. It's at 250 meters, Chandigarh 300, but that probably would be the location. Dehradun over here is at almost 700 meters, so I probably would think that because it's a little higher up into the mountains, it won't be as reflective. But Patiala, I think in this case, is probably the best condition. So I can go in, look at that, click on it, find the location information about that, and then I can go to the station finder and then pull up the data. And in the handbook itself, there are PDFs of this data, but the document can also be in spreadsheet form. And this is what it looks like. The top part, annual heating and design, humidification design conditions, cooling, dehumidification, and enthalpy, and then extreme annual conditions there. And that extreme annual conditions are related to, they're statistically derived, not so much from the period of record, but based on statistics related to the meteorology. If we go on down the page, it is a A4 size page. Then we get into the monthly design conditions, temperature, degree days, degree hours, wind, precipitation, dry bulb, temperature, mean coincident wet bulb, and then wet bulb and mean coincident dry bulb. So you can see the temperature variation there month to month, and when it'll be the hottest, which is as expected normally in kind of May, June timeframe there. So if we're using climatic data and simulation, we need to have some way to represent the climate. And how that's been done has been from a single year, although we have many more years of data. The TMY, or typical meteorological year approach, is most widely used. It's a composite of months, not all from the same year, but they're representative. They're the best January, the best February to represent all the months within that period. There's also an ISO standard related to that. It uses some statistical means to get that from each of the data, and then there are different variations on this. Each has different weights, whether the users think solar is more important or temperature, but often a lot of them use kind of a combined temperature, humidity, wind, and solar measure to give equal weights to get the best fit for that. So we have a year that's supposed to represent the individual. But the TMY data sets are really built to be comparison of alternatives during design or compliance with building energy standards and codes, or getting points of green building rating. They are not necessarily extreme conditions, and that's intentional from what they're doing. And they're not intended to represent design conditions. Although mostly they do a pretty good job in that area, they may not always. Lots of different data sets available throughout the world. You'll see about halfway down, ASHRAE has a data set from a few years ago with about 58 locations in it. ASHRAE's IWEC is in there. Other things, the TMY3 from the US at the bottom. And then recently there's a new data set, open source data set available with 13,000 locations available. And I'll talk a little more about that later. That includes about 100 locations in India. Actual weather data we do need. Typical is good for a lot of the analytics we do to be able to look at impacts of comparative different technologies in compliance. But if we're trying to look at a real building and its energy use, we need the weather data for that year. There are many sources for that. I already talked about NOAA and the WMO data center. That data is available for those stations and it's possible, but there are now a lot of other sources out there, Weather Bank, Weather Source, Weather Underground, all commercial ventures, but they are now sourcing data from many other stations, such as people that have backyard weather stations that are sharing that data there. In my own area, and I'll point that out here in a minute when I show you a graph, but there are hundreds of stations that are small backyard stations that are high enough quality to provide data, but are not included in the normal official record. Also, the National Meteorological offices often have this data available as well for a fee. But the challenge you're always going to have with this is how complete are the data? Does it have what we need? And that's particularly temperature, humidity, wind, and solar radiation. And the answer for most of that is solar radiation is rarely in any of the files. This is Washington, D.C.'s National Airport. It's just across the river in Virginia from Washington, D.C. And this is the period so far that I've found the longest contiguous annual hourly data that I've been able to find worldwide, which surprised me that it was here in Washington. But starting in 1938 through, all this chart doesn't go there, all the way there, through 2018, we have the data for that particular year. So I've got 81 years of data at this point. And what I've done here is taken a medium office building and simulated its energy use for each of those years and then plotted it here. The last bar is the TMY for the area, the typical year. And the encouraging thing is if you draw a line through that, it is doing what it's supposed to do. It is representing that longer period there. I have been doing some work recently on what we call XMYs or extreme meteorological years to be able to bracket those years that are lower or higher. And we have a methodology we're working on, hope to publish a paper in the next year or so on that. Because in Washington, it's a combination, if you look at the bottom of the chart, of the red, which is the heating, and then the blue, which is cooling. And it's a combination of that particular year. 2010 happens to be a particularly high energy year, and it's not because it was particularly hot, but it was a colder year and a hotter summer, not an extreme summer, but it was that combination of things that drove that higher as compared to 2016, which was the hottest year, but was a warmer winter. So this is from Google Earth, a map, and I've got three stations here. This is the DC district right here. Here is that national airport. This is Andrews Air Force Base. That's where Air Force One lives. And Dulles International Airport is out here. There's also a Baltimore airport up here, but you see the kind of the sparsity from here to there is on the order of about 40 kilometers, so not a lot of data. Now, the interesting thing NOAA group here in the US did about 1.5 years ago, they came to Washington and on a very hot day in August, August tends to be hottest, measured temperatures all around the district. And what you see here, temperatures in F, but hot temperatures all over. This is the main commercial ceremonial core of the district. Temperatures that were 5 degrees warmer than other kind of surrounding regions. And then Rock Creek Park is actually a national park that runs almost from the White House north into, this is Maryland surrounding it. And what we're seeing is between Rock Creek, which is heavily forested and never been really logged, and the downtown area is about 10 degrees C difference. And that's kind of the variation you see. And yet we're depending on stations at Dulles and National Airport, which is right here. So it's kind of a huge variation in what is possible. But so heat island is very important to consider as you're looking at this. Moving on to climate change, the Intergovernmental Panel on Climate Change has been publishing a series of groups, and this is the latest from 2013, and they talk about climate change scenarios. Essentially, they are storylines that describe demographic, social, economic, and environmental developments that describe what happens. So it's business as usual, or relaxed regulation, or more intense decarbonization, and each of those has a different impact on the various areas. The latest, the AR5 shown here, being updated right now. I haven't heard when that might be released. The 4 emissions scenarios, the 4 main ones are called representative concentration pathways. They are derived from those 4 storylines and are known by their acronyms RCP 2.6, 4.5, 6.0, and 8.5, and they kind of represent the range. And from that book, you'll see things like this, where you'll see the global average surface temperature from earlier as the historical part, and then what the RCP ranges are. Now, there's a range even for each RCP scenario, in that the data are calculated by a number of different models. It's not just a single global model that you're seeing here. It's all the different models from all the national models from around the world. So even within that RCP 8.5, we're seeing a range of 2.5 to 5.5 degrees C. So there is quite a bit there. So there have been 4 major methods for creating future climatic data. Dynamic downscaling, it's a physics-based model to dynamically downscale what comes out of these global models, which is a full degree latitude, longitude, so quite large, and trying to convert that to something down local scale. Similarly, statistic models are based on the data itself, and they can adjust it based on frequency distributions of there. Both of those are pretty computationally intensive. They're very robust, but there are other methods for getting to future climate. One of the most popular for creating weather files is morphing or adjusting the data in the time series, and essentially shifting and stretching the data to match the predicted monthly change. And that's what I'm going to show you here in a bit, as some examples of that. The other method is more trying to find another station that matches where the predictions from the global models say your location will be in 80 years or whatever the variation is, to find an existing location. And that can be instructive, and doesn't require you to go out and get new morph data or something else to be able to look at a generalized potential impact there. This is from a weather site that looks in kind of change, and they've taken the future data and looked at it and seen there. So what you see is a series of arrows, vectors, that are showing a general trend downward and to the left. And for example, I gave this presentation about 2 months ago, 3 months ago in New York, and showing that New York's climate was going to be much more like Arkansas. So it was going to be, the winter was going to be 4.4 degrees warmer, and it was going to be 10% wetter than normal in New York. So that's one way of doing it. I've seen other ones that the direction of the arrows is much more vertical. So New York might be like Atlanta, for example. So hotter summers and springs and falls all around. If we look at the same thing here, I don't have a website to show me, but I mean, if we were looking at Chandigarh and looking to move down, maybe it's going to Jaipur or Delhi, or looking at other things that are kind of similar in region and climate, taking a look at what the variation there is. I know there's a huge impact of the mountains there, so that may not be quite the difference. That's also true here in the U.S., where we have variation because we have ocean moderating of temperatures, and that could have an impact, so that may not be quite the same direction. Maybe it's going over further to Kanpur or somewhere there rather than to the more arid regions. So I want to show you an example of how the morphing works. From the climate change scenarios, we have an average monthly temperature change, a diurnal temperature change, usually cloud cover change, which allows us to recalculate solar radiation, and then maybe precipitation change as well. So this is and I knew my dog was going to bark, sorry. This is a change from Los Angeles a day in November. Los Angeles has a very nice climate most of the year. The yellow is the existing dry bulb temperature, so starts out in the morning at around 12, 13 degrees, warms up to 22 by afternoon, and then kind of trails off during the day. The other four lines you see there are the climate change scenarios, and what you're seeing is kind of a combination of things going on. There is a base daily range. There's also in each of the scenarios a diurnal temperature range, so that may be a general flattening of that temperature range. Nighttime temperatures tend to remain higher, and there's also the delta temperature range. So it's a combination of things that are changing how that data look on a daily and monthly basis. Heat island is kind of similar from the research that's been done on it. It seems to be a function of population, and I think that's a density issue, not population so much. Roughly 1 to 5 degree on annual average. As you saw in Washington on a particular day, the heat island extremes may be much higher. Beyond about 5 million people, it seems to be roughly 5 degrees. You have enough concentrated building materials and infrastructure and the roadways that are absorbing heat during the day. It tends to depress daytime temperature, bring them down slightly, and raises nighttime temperature. During the day, you're storing heat in all that infrastructure, and then at the night, as the sun's down, then it's re-radiating to the cooler air. So that's Washington Dulles Airport again, a spring day. Yellow again being our existing case, starting off actually below freezing on that day, and then moving up to about 16 or 17 during the afternoon. And that's a spring day, that's not unusual. But the two heat island conditions, you see the red one, which is about 1 degree, staying warmer than that base case, and the blue one, the 5 degree, even more. So I have lower daytime temperatures, that depression that I talked about. The temperatures are remaining higher as the heat is re-radiated, and they remain higher till after sunrise. So here's an example. This is from my local airport. The example predicted change here is for the 4 scenario cases. The typical is on the left, and then the 4 scenarios. And this is monthly energy consumption. And the thing that's easily to see here is that Washington has a reasonable amount of heat, the red bars, mixed with blue throughout even the summer. But as you move to the far right in the scenario there, significantly less heating and much more cooling required, and even into some of the months where we traditionally would not have cooling. And that for a kind of a mid-latitude temperate condition, that's pretty typical. This is source energy, so this is utility meter. If we convert this to just looking at kind of different cases of it, what the impact is that energy use is actually going down at the energy meter. And that's because the inefficiency of the heating compared to cooling is playing into that role. If we look at that as a primary energy, then cooling is back at its full efficiency level, the primary energy taking into account the electricity source. What we'll see there is slightly increased emissions, but not significantly so across the 4 scenarios. The interesting thing is this is a building that uses about 50% less than that base case building, and it essentially mitigates all of the impacts of climate change. So lower impacts are going to actually be reflected better within that low energy building, but even the more extreme cases, we're not going to see increase there. If we go to somewhere extremely hot, humid year-round, Singapore, it's where there's essentially no heating. The source energy is going up in the order of 10 to 15%. That's pretty consistent for that I've seen there. Again, though, a low energy building can help mitigate that impact and just essentially negate any negative change that we're going to see or hotter conditions here. We go to the other extreme. This is above the Arctic Circle in Canada, Resolute Bay. It has a predominant heating load you see there on the left, but the heating's going down. It says a small need for cooling, but predominantly the change there is that it's getting warmer, but not too warm. So we're seeing temperatures up in the single digits, maybe even up to 12 or 14 degrees during the summer there, which it generally doesn't get above 5. So huge swing in temperatures, much less frozen periods for that. Also, if you same sort of mitigation for the low energy buildings. And if we move to Delhi, kind of the same sort of idea. While this is showing that there might be a slight need for heating, generally there's not a lot of heating there, as you know. But what we're seeing is similar to what we saw in Singapore, is an increased need for cooling for the other cases. That's at the site energy level. If we go to the source energy, it's even more. So we're seeing on the order of 20% more case. And in locations like Delhi, where the electric loads are already quite close to the limits, this is going to put an even increasing load on the electrical system. The good news is if we put low energy buildings in, that increase will be less. And so that's an opportunity for us to have our better buildings continue to operate and not bring the grid down. Heat island in Delhi, kind of similar sort of impact, a small increase in change on source energy, and that heat island can be mitigated again with the low energy buildings. The largest changes that we're seeing, though, are at the monthly level, and that's where you can see. So the bottom left, I've got Washington Dulles Airport again that we saw earlier. The bottom right is Singapore. Top right is Sao Paulo, where there's a little bit of need for heat in the winter, although they don't typically heat in Sao Paulo. But you see across the board an increase in cooling there. And then top left, Egypt, where it actually gets cool enough to need heating, kind of the November to February timeframe. It is significant increase in the in the energy use on the order of almost 20% for Cairo, that the temperatures there are going to get quite a bit hotter. I don't have a similar chart for Delhi at this point, but at least I couldn't find it quickly. But what you're going to see is a real change overall toward more cooling demand throughout the year and less interest in heating. So with that, I'm going to take it to the summary. We need climate data. It's critical for us to be able to correctly size equipment, to be able to know what the loads are going to be, so our systems to be able to meet the needs of that system that we're creating for human comfort in our buildings. If we're doing building performance simulation, the typical TMY, actual and even future weather can support this. I'm not a real fan of people doing a lot of work to do sizing toward future design, because most of the equipment that we're putting in our buildings today have a life on the order of 10 to 20, maybe 30 years if we're lucky. And that over that period, the temperature change, as you saw from the design conditions, is not a lot. So there's some, I don't think you can take a look at it, but I don't think you want to design. Our design calculations already have enough oversizing in them. I also mentioned the X and Y idea of looking at the extremes to try to bracket what the possibilities will be, and hope to have something on that soon. There are great sources of data now available. The ground observing stations becoming more robust by day, and satellite data as well, with that reanalysis product that should come online hopefully later this year, NASA thinks. So we could represent these climate change scenarios by modifying files, the morphing method. If we use that, we can see the building in the higher latitude climates will see significant decreases. Heating decreases more than cooling. Tropical, semi-tropical will see increases, but they won't be quite as severe, partly because there's already significant cooling load there. If we go with energy efficiency or even to zero energy buildings, this is going to mitigate most of that impact. It also will help meet the loads better for these buildings as they're trying to use renewables. And overall, the result is significantly more hours of cooling equipment operation. So that's a real challenge there. And that's something I'm looking into now is what sort of increase in hours of operation we're going to see, not just the energy impact, but is there equipment going to, instead of operating 3,000 hours a year, is now going to be operating 4, and that'll reduce the life of the equipment, obviously, very quickly. So if it's changing, what should I do? Well, start off by designing the best building you can, going beyond energy codes, looking at things like zero energy or the well building standard, 2030 challenge here in the US, other activities in your locale that are really pushing to take you beyond code. Building equipments and components have a relatively short life. Don't try to design for 2100. Even if the building will still be here at that point, it will be quite different in that time. There'll be a lot of changes for its use and its equipment and systems on that. But plan for future upgrading. Make sure that it's possible to do that. If you're worried about the impacts and have a client that's interested in that, take a look at the next warming climate. Maybe it's taking Chandigarh to Jaipur or Delhi to Mumbai. I know that's taking it more tropical, but take a view of what you think the next hotter city might be, and look at the design conditions. How different are they? Are they a couple degrees or more extreme? We have sizing and oversizing factors built into our calculations. A lot of the studies I've seen where they've done measurements is that buildings rarely ever get to peak condition, that they're generally 20 to 40% oversized. So we have a lot of slack in that capability already, and it's unlikely in the life of the equipment we'll get to that. If you're doing simulation and you have the possibility to get a future file, great. If not, just take that next warmer climate again, just like looking at the design conditions. So finally, I want to talk about metrics, and this is kind of a general thing. My career kind of focused around this when I was starting: energy use, energy performance, peak demand, energy costs, capital costs. Those were the metrics that we used to really look at it. And we always looked at them in terms of normalized per square meter and trying to see how that looked compared to other buildings. But as I've continued to do my work over the last 15 years, particularly working in zero energy, we don't really look at some of these other metrics such as water, indoor environmental quality, or even carbon emissions. We're going to miss opportunities and also maybe make a building that's going to have negative impacts. There was a project that we did some analysis on when I was at Department of Energy that did not really look at peak demand and wound up with energy savings of 75%, which was spectacular at the time, but the energy cost savings were only 34%, because the control systems were not locking out systems that were abnormally affecting peak demand and energy costs. So you need to take all of those in case. But the other thing I've learned is that it's important to understand the business model of the owner, the group, that you're working with. Theirs is probably not a normalized to floor area sort of metric per square meter. If it's a school, they're probably interested, what does this building cost me to build in terms of per student, or what savings? So if you can say, I can save so many thousand rupees per student a year, you probably get their attention. If it's a hotel, they talk in terms of revenue per occupied room. And so they don't really think of it as a floor area for that particular case. If it's retail, yes, sales is normally measured on a per square meter basis. The most interesting ones I found is both a brewery and a winery that were reporting their carbon savings in terms of how much they save per case of wine or per barrel of beer they produce, because that was their metric. And so it's important to understand the metric to be able to talk in the same terms that business owner may talk. I want to point you again to the data set for those the new typical about 100 locations in India today you see spread throughout. Those are available from download at climate.onebuilding.org, free open source data available. And with that, I'll stop and thank ASHRAE, ISHRAE, and ABIPSA for hosting and letting me share this with you today. Thank you.
Yeah, thank you very much, Dr. Drew. Since a great presentation, which have covered the heat island and weather data analysis and what are all impacts the building energy performance. So that was a great presentation. So we will quickly take few questions from the audience that we have as of now. So I'm just proceeding with the first question, which is, what is the order of matching between satellite data and data from ground measuring stations? Is there a significant mismatch? How to modify the weather files that are largely based on satellite data?
The satellite data actually match the ground station data pretty well. That's one of the things that NASA, in a project, it'll be a publicly available website, hopefully later this year, called POWER, P-O-W-E-R, and they are doing the analysis to make sure that the data, I've got some of their data files from 30 locations around the world right now, trying to look at not only a typical file, but actual individual years. Initial studies I did, I got data for the 2 airports near me that I talked about, Washington Dulles and Washington Reagan, the one where I had National Airport, where I had the 80+ years. It matched the individual hours almost exactly at Dulles, at the more land-based one. National Airport is next to a river. It's moderated in many respects, and because of that, anywhere you're near a body of water, the satellite data does not work as well, and that is something we are seeing. But otherwise, it is matching quite closely within a half or a quarter degree in most cases.
Okay, perfect. So yeah, next is what are the prospects of using thermal energy storage in passive building design and use of PCM walls and activated concrete for reduction of energy bills in the next 10 years?
Okay. Storage has a huge opportunity. It's not a energy saver so much as it is to help reduce cost, because you're producing that energy normally when it's cheaper, the utility costs are lower, it's not peak demand, and then you reuse the energy out of the storage where it's cooling or heating. PCMs are very effective in buildings where you have a temperature swing. If you're holding temperature in, for example, an office building within 21 to 26, there's not a lot of temperature change within that would help PCMs work. But if you're doing a broader range of maybe 15 to 30 even, then there's some opportunity for PCMs to help moderate that temperature and store heat as in the hotter times and release it when it's cooler. So they have their place, but I would say in kind of modern air-conditioned offices, they're not as effective.
Perfect. So yeah, that sounds good. So next is for city level, if UHI mitigation measures are well planned and implemented, can this reduce future energy consumption of the buildings located in city? If you can consider it in for next 20 or 30 years of time period.
Yes, if I understand the question correctly, you're asking if we can do some mitigation of the heat island effect, and
Yes.
the reality is yes. We talk a lot about green roofs and other things to reduce the impact of our buildings, but if you look at the ratio of the paved areas, the streets, the sidewalks, the parking lots, compared to the building area, it's usually a factor of 2 or 3 more. And so if we can do things that will reduce that storage of heat in those elements, either reflectivity or shading them or other ideas like that, we can significantly reduce the heat island.
Yeah, perfect. So yeah, thank you very much. As the time skips, so we have a few questions that all have been resolved. So yeah, thank you very much at the end. Now I would like to invite Mr. K.K. Mitra from ASHRAE India chapter to share his views and a vote of thanks from ASHRAE India chapter, please. Sorry,
Mani, I think there is. So let's proceed.
you're not audible, sir. So you are not audible.
Monica, am I audible?
Yes.
Now you're audible, no? Okay.
Yeah.
Okay, you can see the screen also?
Yes.
Okay. So it was a lovely presentation, Drew, and you very nicely shown about the Indian cities and the effect of high temperature. I will just have a quick presentation regarding the effect of the building envelope and how an insulation plays an important role. So basically, one of the important factor which I wanted to show in India, especially northern India, where we get very high temperatures, ambient, and in fact, just 2 days back also, till 28, we had a very, very high temperature. So I start my presentation, though it's very long, I'll just cover the important ones. If you see, typically in northern India, when we have ambients crossing 40 degree, and typically when we have a civil construction with your RCC and the brick walls, which is typical the construction engineering, your actual roof temperature goes very high. It's almost, you can say it is 10 to 15 degree more than the actual ambient. So what happens is that when the temperature is there and the heat is absorbed by the roof, it is conducted inside. When it is conducted inside, you can imagine that the temperature goes very fast immediately. And when you're actually trying to maintain a temperature of say something around 22 degrees or 24 degrees for air conditioning, and if it is a non-air conditioned 32 degree, so a huge amount of energy is required if you're running a air conditioning machinery. Or even if you're not running an air conditioned machinery, as in present situation, we say that we have to live with fresh air. So the delta T is very high. So that is a big challenge what the building envelope in the northern India has to take care when the ambient goes up. If you typically look at this particular slide, it is in fact the month of May. In fact, when your ambient is around 42, 45, in fact this year it returns to 46 degree also in Delhi. And because of the low humidity, if there is a rain like what we had in the last 2 days, the ambient comes down. So 42.6 may come down to even 18.7, 20. So this was particularly some couple of years back. So huge amount of energy goes to the roof. And typically around say statistics says 24.6 kilowatt hour per meter square. Wall, the solid cover of the bricks, it is 8.1. So these are the two factors which actually needs to be controlled by proper insulation. So in this particular presentation, I will just take you around about what the impact of insulation can be on the building envelope and how the reductions are possible. So when you talk about an envelope, we are talking about the roof and the wall. And you provide an insulation, we try to create a resistance. And by this resistance, we try to bring down the temperature by 8 to 9 degrees centigrade. By proper selection, the method can be your Energy Conservation Code of India, what we have, or National Building Code of India. So they give the various U values by which you try to calculate the thickness. And we create this barrier, and R is equal to L by K, and the temperature is controlled. And in fact, this is basically a simulation activity. I will show you a slide also, that each and every construction item of a building, roof and wall, acts to some sort of a reduction in the temperature going inside. And when I come back to the original slide which I showed there, you can actually cut down the heat induction through the roof by 90% by going for a proper insulation. Similarly, the wall, it can be cut down to 70%. So U value from 4.2, it comes down to 0.261, which an ECBC code says for energy efficient building, and 2.1 becomes to 0.44. So that is the impact of insulation when you have on the building envelope. And this has a directly impact on the energy conservation requirement for the air conditioning machinery also. So this is a graphical representation of the gap. So you can see the ambient, which is almost touching 44 degree with a good insulation, you're trying to bring down the temperature to around 32. Now, why 32, 34 degree we talk about? Because in a typical tropical country, human beings can sustain 30, 32 or 34 degrees centigrade and carry out their normal working. The moment it crosses more than 32 or 34, you feel oppressive, and when the humidity increases, it becomes impossible to work. So that is how this slide works out, that when you have the ambient for a typical office building, which is running from 10 o'clock to 6 o'clock, so you are having two types of temperatures. One is the working floor temperature without insulation, and a working floor temperature with insulation. So different category of insulation, you can go for fibrous, for rigid insulation, and you can go for the temperature control to around 30, 31, 32 degree centigrade. There can be various methods by applying insulation. Even when you have a beautiful claddings, architectural, you can fill the cavity with insulation. You can spray insulation on the roof and wall. So various methods are available there.
Yeah.
The important target of it is that you try to cover the entire building with a cover. And what is practical and what is more effective is that if you're able to insulate your building envelope from outside, because if you're doing it from outside, then you are actually stopping the heat right at the source. So your mother roof and brick wall does not get heated up. So there are various methods, are various pictures are showing those applications there. Now, one of the important factors have these type of claddings. Another property of this building envelope is that these cavity, why it is needed to be filled with insulation. So apart from thermal, one more factor comes in is your fire propagation. Like what happened sometime back in the Grenfell Tower in the London. So this building, beautiful building, has a aluminum cladding system, but the cavity was not filled with insulation. So when there was a fire, this cavity filled with oxygen, the fire raised very fast. And whenever the windows are open, curtains are there, the fire goes inside. So here insulation also plays as a fire protection. I talked about the building envelope insulation doing from outside. Now this particular slide shows that the roof actually has an insulation outside, which makes the RCC cool roof. Similarly, the brick is called cool brick wall. Now what is the advantage? When you're running an air conditioning system, these cool roof and cool brick wall actually acts like a cold storage. It absorbs the cold and reaches an equilibrium stage, and after some time it is radiated inside. That is where you get your energy conservation. So this is how the building envelope can be protected in a typical tropical place from the high ambient coming up. Another method, suppose you're doing it from inside. Suppose it's a large building and you want to have the portion of the building envelope controlled to stop the heat from coming inside. You do the same application from inside. So your hot RCC and hot brick wall does not get in touch with your cooling system. So this is the impact of building envelope insulation in terms of what environment ambient conditions is there. Now this is a particular simulation site which is done as per the Energy Conservation Building Code of India. Now here what is shown is that you start from the outer surface. It can be the cladding, it can be your plaster. So you start with 45 degrees temperature. And as you gradually move up, there is reduction in the temperature. Maybe it can be 0.1, 0.4. But when it touches the insulation layer, the green line shown here, there's a huge reduction in the temperature. So this is the impact which happens. So this is particular for one category of insulation. Similarly, another category of insulation is also possible with this. Same thing you can do for wall also. So such type of simulations are possible, and by which you can work out a proper selection methodology of a material, what is the temperature we are getting inside, and so on. We have our Energy Conservation Code of India, which it was modified in 2017. It was originally made in 2007. Country India is divided into 5 zones and U values are provided. Now gradually, after 10 years, it was felt that building envelope allows almost 70% of heat energy to come inside. Cold is also there, but since India has got almost 7 to 8 months of high ambient condition, stopping heat is more important. So they have now modified the category of building into energy efficient or SEE, super energy efficient. So building can be a daytime use building, it can be a 24-hour use building. And you can see there's a gradual, very high reduction in the U values. So it is recommended that a good insulation plays a very important role in keeping the inside conditions much cooler. This is for the roof and the wall. Yeah. We also have got a very good document, National Building Code of India, which has a sustainability chapter. This particular slide shows the various permutation combinations of a building roof with various kinds of insulation materials available in the country, and what can be the possible U values. If you see the red marks shown here, you can actually come down to a U value of 0.2, which is in the category of energy efficient as per ECBC 2017. So our country, we are more and more graduating into energy savings by passive methods. That is most important. I'll just show you one case study. This is in a place where Dr. Jyotirmay Mathur stays, that's in Jaipur. So this is a building called Aranya Bhavan, and this building has got a traditional stone cladding. Jaipur is a place where ambient touches almost 48, 49 degrees centigrade. So this building was targeted to make energy efficiency savings 32%. So it's called before Sharath and after Sharath. Before Sharath is something where you don't have the energy conservation method. So it was coming to energy performance index of 77 kilowatt hour per meter square per year with an investment of 30 crore. After the various methods of energy conservation like insulation of roof and wall, double glazing, centralized water cooled chiller system, the building EPI came to 53. Cost went up marginally by 0.6 million. But after a year, the EPI actually worked out to 43. So you can see almost nearing to 45, 46% the savings is possible. Now something I also tell you about net zero buildings. Net zero buildings, if also provided with insulation, like this particular building, which is world's largest net zero building located in India, which is 30,000 square foot, have been able to get very good energy conservation aspects. In fact, now before closing, I will just cover about the COVID-19 pandemic. We talk about the conditions which is actually required to stop the spread or to reduce the spread of this disease. Now we talked about insulation, envelope insulation, and you try to get interior temperature for ergonomic comfort 31, 32 degree as presented earlier. Suppose you're looking for air conditioning 24 to 27 degrees centigrade, that is possible. If it is evaporative cooling, where low humidity is there, we have 29 to 30 degree. So this is in relation to ambient condition of 40 degree. Now when you talk about insulation, now if you see,
Yeah, sir, its time is actually.
Yeah, without any air conditioning, the envelope can bring down your ambient to 31, 32 degrees centigrade. So if you're going for air conditioning, your delta T is just 2 to 8 degrees centigrade. So that is the amount of machinery required to cool down. And since 1 degree drop in temperature is equal to 3% extra energy is consumed, so you can imagine that if the building is not insulated, you have to bring down from 40 degree to 24, 27 degree. And when you talk about building envelope, how COVID-19 spread is stopped is that we have a document ASHRAE who has come out which says guiding document for air conditioning ventilation. So that document also says that you have to maintain 30 degree temperature or more or humidity of 80%, but those are ideal conditions. But practically we try to keep 24 to 30 degree and 40 to 70. So what I want to highlight before I close down is that the building envelope insulation can actually complement to the cooling arrangement in this COVID-19 pandemic situation and give a very good climate insight. So with that, I close, and any questions I can take it up. Otherwise, you can give it to Moni. Moni will forward. Thank you.
Yeah, thank you very much, sir. Now I would like to invite Dr. Vishal Garg from IIT Hyderabad, who will represent IPSA India and share vote of thanks to Dr. Dhruv Kroll, please.
Yeah, thank you, Mani. On behalf of Indian chapter of IPSA, I thank Dhruv for such an informative presentation. Dhruv, you started from the fundamentals and covered a lot of ground. It is really remarkable that with such a nice pace. You covered right from the fundamentals to all the detailed aspects of your talk. I'm sure this talk will be helping everyone, right from the beginners to experts. And I also hope that climate change aspects are going to be considered in the building designs and in the building energy codes in India. I thank the organizers for this very timely talk. About 350 participants attended, and I understand that the recording will be available and many more would be benefited. I'm sure this talk will motivate researchers and practitioners, and they would consider climate change in their work. Thank you very much again for sharing your research and your valuable advice. Thanks a lot, Drew, for your time. Thank you.
Thank you very much, sir. Now we are signing off, and we just sharing information that ASHRAE Annual Conference 2020 will go virtual this time, and 92 technical session for just 99 you can join and register today. So our next, thank you very much. These were the co-organizers and association. This was organized webinar, and our next webinar is on 6th June, which is on sustainable infrastructure for green communities. Mr. Daniel Echnal, ASHRAE DL, who will be representing this topic. Thank you very much. We are signing off, and thank you very much for support, completely support from IPSA India and ASHRAE Thane chapter, ASHRAE Delhi chapter, ASHRAE India chapter from Mr. KK Mitra have represented, and Mr. Manish from ASHRAE Thane chapter, who have shared his valuable contribution to make this event a huge success. And once again, thank you very much, Dr. Crew, for your sparing your valuable time and sharing very deliberated information with all the participants. Thank you very much.